In this video, we're going to talk about colligative properties, okay, which is out here. So the question is, what exactly are colligative properties, okay? Colligative properties are any properties that depend on the number of particles in solution, okay? Number of particles, but not on the identity of particles. So, for example, let's say you go to a market and there's going to be a lot of folks out there in the market. Now, if there's a lot of folks, you're probably going to experience the effect of a crowd. Maybe a better example is, let's say you go to a concert. There's going to be a crowd at the concert, okay? Now, the excitement of the crowd is not dependent on each individual, but basically what you experience is a collective effect of the number of people at that concert. I hope that makes sense. Now, with respect to colligative properties, there are actually 4 colligative properties that we're going to learn. Let me kind of write them down. The first one is vapor pressure lowering. The second one is freezing point depression. The third is boiling point elevation, and the fourth is osmotic pressure. So there are 4 colligative properties. The first one is vapor pressure lowering, the second is freezing point depression, the third is boiling point elevation, and the fourth is osmotic pressure. Now the thing about these colligative properties, the second and the third colligative property, they actually depend on the first colligative property. So if you have a good understanding of vapor pressure lowering, it helps your understanding of freezing point depression and boiling point elevation quite a lot, okay? So let's start our journey with trying to understand what exactly is vapor pressure lowering. So in order to understand vapor pressure lowering, imagine that you have a solution out here. This is your solution, all this area, okay? And the blue is your solvent, and then you have a solute that is dissolved in that solvent, which is a non-volatile solute, which means the solute does not go into the vapor form, okay? So now if you imagine the surface of the solution, you're seeing there are some solute particles, and you can think of them as, because they're not able to go into the vapor form, they're actually blocking the solvent particles right below them from going into the vapor form. So you would have had more vapor out here, but you have less because of the blockage that is being put into effect by the non-volatile solute, okay? So as a result, you have a lowering of vapor pressure. So this lowering of vapor pressure, let's try to understand exactly. If it was a pure solvent, okay, let's say the vapor pressure of the pure solvent is P naught. So we're going to say P naught is for the solvent. Let's call the vapor pressure Vp of pure solvent. And then now what's happened is the vapor pressure of the solution, okay, which means when this got mixed together, that vapor pressure, it actually went down. So let's call that P of solution, vapor pressure of solution. So now the difference in vapor pressure, recall, if there was no solute out here, then you'd have more vapor molecules in the vapor state, okay? So therefore, this vapor out here is exerting a pressure downwards on the liquid. That's really vapor pressure. Because you have less vapor pressure because of the blockage by the solute particles, you can say that the change in vapor pressure, we're going to call that delta P. This is also called lowering of vapor pressure. is equal to vapor pressure of the pure solvent, so that's P naught solvent, minus vapor pressure of the solution. Okay. So there is a law called Raoult's law, and Raoult's law states that the vapor pressure of the solvent is going to be dependent upon the amount of solvent particles in the solution. Okay. And so how do you define the amount of solvent particles? You can just define it as a fraction of the total number of components in the solution. So imagine that this is a two-component solution, solute and solvent. So then what fraction of the solute and solvent are solvent particles? And that fraction is defined as the mole fraction. So if you take the mole fraction of the solvent and you multiply it by the vapor pressure of the pure solvent, that is going to equal to the vapor pressure of the solution. Okay. So according to Raoult's law, P of solution is equal to mole fraction of the solvent times P naught of the solvent. Mole fraction of the solvent means how much solvent is there proportionally times the fraction of the entire, times the. So now if I take this and I replace this term in this expression with this, then I get delta P is equal to P naught solvent minus mole fraction of the solvent times P naught solvent. And I can kind of deal with this algebraically. So what I'm going to do is I'm going to clear up some of this, and I'm going to take this expression and I'm going to take it forth from there. Okay, so what we have out here is this expression. Now I'm going to take this term common, and I'm going to break this down. So if I take P naught solvent common, then what I have left out here is just 1 minus mole fraction of the solvent. And then this actually ends up being the mole fraction of the solute. 1 minus mole fraction of the solvent is equal to the mole fraction of the solute. So this becomes times mole fraction of the solute. So if we use Raoult's law, the vapor pressure lowering, or the change in the vapor pressure, is equal to the vapor pressure of the pure solvent times the mole fraction of the solute that we use. Now, if you're unable to understand what the mole fraction of the solute means, so let's imagine you had a pizza out here and you cut the pizza into 4 slices. So that's the whole. So the whole pizza is 1. But let's say you took just one of those quarters. So that would be 1/4. And then let's say one of you ate. So let's call that A. So A would be 1/4. And then person B ate all the rest. So if you add those together, you get 1. But if you had to figure out how much did person B eat, so person B ate 1 minus 1/4, which is similar to this expression, which would be 3/4, which is the same as what person B ate. Okay, so we apply that same logic out here to kind of figure out the mole fraction. So now let's talk about what if our solute was actually a volatile solute. That means that some of those solute molecules would actually be up here in the vapor form, which means this total vapor pressure that is pushing down on the surface of the liquid is going to be having a contribution from the solute vapor molecules as well as the solvent vapor molecules. Okay, so then we'd have to modify. So if that is the situation, then we'd have to modify the total vapor pressure, let's call that P total, that is going to be equal contribution from both those components. So that is going to be mole fraction of the solute times P naught of the solute, that is the vapor pressure of the pure solute, plus mole fraction of the solvent times P naught of the solvent. Let's try to understand what freezing point depression is. So if you pay attention to this diagram out here, you'll see you have a solvent, which is the blue, and then you have the solute out here. Now, if you're trying to freeze this, in the absence of the solute, you're going to observe a certain freezing point. Okay, so let's call that freezing point of solvent. Now, because there is solute in this, when things freeze, the molecules tend to come close together. But now imagine there's these little red dots, which are the solute particles, that are preventing the molecules from closing in, which means you have to kind of squeeze them harder. What that translates to is you have to depress the temperature even more. Okay, so if you take the freezing point of the solution, okay, so you depress the temperature, you squeezed out, you pushed out the red little particles, and then it froze. That is equal to, so the freezing point of the solvent minus freezing point of the solution is equal to Kf, so that's a constant, which is called the freezing point depression constant, also known as cryoscopic constant. Also, let's write that out, freezing point depression constant. And this constant is specific to the solvent you're using. So water would have its own Kf value. If you're using ethanol, that would have a different Kf value, and so on, okay? And that's multiplied with the concentration expressed in molality, okay? So times small m. That is the concentration in molality, okay? So this entire thing can be condensed to write the change, so delta Tf, which is the freezing point depression, is equal to Kf times m, the molality. Let's try to understand boiling point elevation. So if you actually had a solution and you had some solute particles in the solution, you heat the solution till it reaches to the point of boiling, and if the solute particles were not there, then there would be no barrier to the molecules going up into the vapor form. But because of these little red particles on the surface, what's going to happen is you'd have to give them more energy to push the red particles out of the way to go into the vapor phase, okay? And so as a result of that, the boiling point of a solution will increase when you add particles to it. And you can try that at home. You take a pan of hot water, water, crank the heat up, it starts to boil, and then just add a bunch of sugar to it, for example. Or you can add salt, and you'll see the boiling will cease, and it'll restart again after some time when the heat increases. All right, so the expression for this is the change in the boiling point. So let's call the boiling point BP. Boiling point of the solution is going to be higher, so boiling point of the solution minus boiling point of the solvent, okay, because that difference is going to give you a positive number. That is equal to Kb times molar concentration m. Molar concentration. That Kb is called the boiling point elevation constant. This is dependent on the solvent. So if you have water, it'll have a different value of Kb. If you have ethanol, it'll have a different value of Kb. Okay, and then another term for this is called ebullioscopic. E-B-U-L-L-I-O-S-C-O-P. Ebullioscopic constant. Okay, you'll probably see this more often, but you might see this in some old books. So this entire thing can be condensed to a form of delta, so that's the change in boiling point is equal to Kb times m. And you'll have to use this formula in a lot of problems. Let's talk about osmotic pressure. Okay? So let's pay attention to this little U-shaped tube out here. You have two solutions in this tube separated by this little membrane, which is called a semi-permeable membrane. So this line out here you're seeing is a semi-permeable membrane. And what a semi-permeable membrane does is it prevents certain molecules of a certain size to get through it. Okay, so it's selective. And when it comes to osmosis and osmotic pressure, we separate it by a semipermeable membrane that only allows solvent molecules to pass through but not solute molecules. So if you look at the two solutions on both sides, you can see there's more red dots out here than out here, so that's less concentrated and that's more concentrated. So let's write that out here, more concentrated, and that's less concentrated. Okay, so what's going to happen is, because of this difference in concentration, the solvent molecules are going to want to pass through to kind of equalize the concentration, because out here you have a greater ratio of red to black, so therefore they want to pass through, and they'll keep passing through till the concentration in both sides of the tube are the same. So if you direct your attention to this tube out here, now the concentration is same on both sides. And as you can see, as a result of the solvent molecules passing through, the level actually went up here and the level went down here. Okay, so the difference in level, they kind of draw a line from here to here. This difference, there's a difference in level created. So if you actually went out here and you put a little piston out here and you pushed down, so you exerted some pressure, you pushed down, you'd be able to push it back to the level it was at, and even furthermore depending upon the force, but you basically want to push it back to where it was, which is the initial situation. That would be the osmotic pressure. Okay, that means what we're saying is that because of this difference in concentration, there was a net pressure out here. Because of the osmosis that took place out here, there was a net pressure where the solvent molecules passed through the membrane to equalize the concentration. Okay, and that pressure is the osmotic pressure. Now, how are you going to express osmotic pressure? We use a capital pi, which kind of looks like this. Okay, that's called a pi, but it's a capital pi. Okay, that is equal to m, the molarity, times r, which is the ideal gas constant, times T, the temperature. Okay, and R, the value of R in this case would be 0.08206 liter atmosphere per mole per Kelvin. Okay, so that's what you're going to use. Key point of distinction out here, when you're doing freezing point depression and elevation of boiling point, you will always use molality for concentration. When it comes to osmotic pressure, you will use molarity. Okay, so if you don't understand the difference between those two units of concentration, you might want to go back and refresh those basics in terms of what are the formulas for molarity and what's the formula for molality. Let's talk about the concept of a Van 't Hoff factor. Van 't Hoff factor is given by I. I is defined as the moles of solute particles divided by the moles of formula units. So what this means is, if I take sodium chloride, for example, if I take 2 molecules of sodium chloride and I dissolve it in solution, the expectation is that I would get, the effect is going to be from those two molecules of sodium chloride. The reality is that this sodium chloride is composed of 2 ions. So the second you dissolve it in water, one sodium chloride splits into 2 entities, this one and this one. Therefore, for 2 molecules of sodium chloride, you should see 2 times 2 is 4. So you'll see the effect playing out as if it was 4 molecules of sodium chloride you put in there. The reality is the sodium chloride split. If you recall our definition of colligative properties, we don't care what it splits into, we don't care what the molecule is, we just care how many entities or how many particles are present in solution. Okay, so how do we apply this? Well, number one is we can have a measured value, an expected value. So the expected value for sodium chloride, so for 1 unit, the expected is 2. However, we don't often see the expected value. What we actually measure is for sodium chloride be something around 1.9. Okay, and what that means is that sometimes if you have a big bucket and you have all these sodium plus and Cl minus ions and they're surrounded by molecules of water, okay, what's going to happen is there are going to be instances where a sodium plus is going to find a chloride and stick to itself. So those are called ion clustering, okay, or ion pairing. And because of that, this is going to appear as one unit, okay. But of course, since the solution has many molecules out there, some of them are going to appear as one unit because they come close to each other, but most of them are going to not appear as one unit, but as the split ions. So as a result of that, it's going to be close to 2, but not quite 2, and you'll see a little depression, okay. So there's a difference between expected and measured. Now, how does this apply to some of those colligative properties we learned about? Vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. We just put a little I to the left of the formula. So when it comes to vapor pressure lowering, we do delta P, that's vapor pressure lowering, is equal to X solute times P naught of solvent, and we put a little I out there, and this I is dictated by the solute we're concerned with. Freezing point depression, delta TF is equal to I times KF times molality. Boiling point elevation, delta TB is equal to I times KB times molality. And osmotic pressure, pi, is equal to I times M or T. I hope that made sense.